All right, we're going to talk about Chapter 10. And in Chapter 10, we're making a transition. We've been dealing a lot with mass and velocity and momentum and changing, and we're gonna slightly ease out of mass and velocity, and we're gonna start talking about energy for the next handful of chapters. Now, energy is related to uh, energy is related to mass and velocity. We'll continue using those, but now I guess we're gonna throw in energy. And when we talk about doing energy, we first have to start with work. What is work? Work is just the force needed to move any object. So the force needed to move any object is work. The equation for work is equal to force times distance. F being force units being in newtons, distance being d, the units being in meters. The unit for work and the unit for energy, in which we're going to have quite a bit, is joules. So the unit for work and the unit for energy is joules. And work is equal to force times distance. Now, that equation works if we are on a flat surface. The force times distance works if we are on a flat surface. Anytime we incorporate an angle into our units, or when we're trying to solve for work, it's going to add the cosine of theta. So anytime you're trying to figure out work either on an inclined plane, or I'm pulling a wagon with the handle being at a certain degree, that's going to change my unit for work. And in that case, work is equal to force times distance times the cosine of theta. So you're going to have to add that theta angle in anytime you are not going on a flat surface. So work is equal to force times distance on a flat surface. On an angled surface, or when an angle is involved, you have to add the cosine of theta. Now, we mentioned in Chapter 10 that we are talking about kinetic energy, or we're just talking about energy in general. The first type of energy we're going to talk about is kinetic energy. And kinetic energy is energy in motion. Now remember, energy in general is just the ability of an object to produce a change in itself, whether in momentum or velocity or anything around that, and change the surroundings or the environment around it. And where we start is kinetic energy. And kinetic energy is energy in motion. So a lot of times we'll abbreviate kinetic energy with KE. KE is equal to 1/2 mv squared, m being mass, v being velocity. Now, just as mentioned earlier, the unit for kinetic energy is joules, because our base unit for energy is the joule a lot of the time. So our unit for energy, kinetic energy, is joules, and our energy for work is joules. And what we can do is, since they have the same unit, is we can tie them together in the work energy theorem. And what this equation says is when work is done on an object, the result is a change in kinetic energy, which means this equation, work is equal to change in kinetic energy. So if I solve for work, I can also solve for kinetic energy, or vice versa. So what we'll do is we'll take a look at a couple examples, apply these equations, and talk about them. So in the example here, we have two examples. Example number 1, a 105-gram hockey puck is sliding across the ice. A player exerts a constant 4.5 Newton force over a distance of 0.15 meters. How much work does a hockey player exert on the puck? And secondly, what is the change in the puck's energy? Well, we are on a flat surface. We are on a ice rink, so our work is equal to force times distance. Our force value is 4.5 newtons. Our distance value, or D, is 0.15. Multiply those together, and we end up getting 0.675 joules. The second part of this equation is asking what is the change in the puck's energy. Well, remember, work is equal to a change in kinetic energy. Remember, triangle equals change. Our work was 0.675. If our work was 0.675, our change in kinetic energy is also going to be 0.675, since they are equal to one another. So using that equation, work, remember that work and change in kinetic energy are equal to one another. Next up, question number 2. A sailor pulls a boat a distance of 30.0 meters along a dock using a rope that makes a 25-degree angle with the horizontal. How much work does a sailor do on the boat if he exerts a force of 225 newtons on the rope? Here, we have an angle coming into play when we solve for work. When we have an angle coming into play, we're going to have to add it. So work is equal to force times distance times the cosine of theta. So work is equal to force. In this example, our force was 225 newtons times our distance, which was 30.0 newtons, times the cosine of 25 degrees. Just a friendly reminder to make sure your calculator is in degrees instead of radians. Multiply those out and making sure we have 3 significant figures. Our final answer is going to be 6,120 joules. So 6,120 joules applying that unit of force. So remember, work is in joules, and in the second equation, we plugged in our angle. Last thing that we have to talk about for section 10.1 is power. And power is simply how efficient you are doing work, or the rate at which you're doing work. So how fast or how slow you are doing work. And that is power. So power is how fast or slow you're doing work. Power is equal to work divided by time. P is power, W is work, T is time. If we go through units, we know the unit for work is joules. We know the unit for time is seconds. Our unit for power is watts. And sometimes you'll often see a kilowatt. And a kilowatt is simply just 1,000 watts. So if we take this equation and tie in everything that we've done to get an example for 10.1. An electric motor lifts an elevator 9.00 meters in 15.0 seconds by exerting a force of 1.20 times 10 to the 4th newtons. What power does the motor produce in kilowatts? So we are going to try to solve for power. Let's look at what we have. We have our distance is 9.00 meters. Our time is 15.0 seconds. Our force is 1.20 times 10 to the 4th newtons. What power? So when we try and solve for power, remember power is equal to work divided by time. Well, we have time, but we don't have work. But we are able to solve for work because work is equal to force times distance. Well, we have both force and distance. So our force is 1.20 times 10 to the 4th. Our distance is 9.00 meters. Multiply those together, and you get 1.08 times 10 to the 5th. We're going to take this value now, and we're going to plug it into our work equation. So we're going to know 1.08 times 10 to the 5th was our work. Remember, the unit for work is in joules. Divided by time, 15.0 seconds, and we end up getting 7,200 watts. However, remember, the answer needs to be in kilowatts. So to put this answer in kilowatts, we'll divide by 1,000, and our answer is going to be 7.2 kilowatts. So we will continue with work and energy, and what our focus is going to be on is machines. Simple machines, compound machines, how machines work, and how efficiently we can use work and power. But with that, that is the end of section 10.1.